Okay.
Hello, everybody. Welcome to the CSE departmental seminar for today. I just want to give you a reminder that we actually have another seminar tomorrow at 2 p.m. In Cruth 179. Joe Catapano from ICANN is going to be here. So the reason that we are so fortunate to have all these good speakers this week is because in Dallas this week is the IETF Internet Engineering Task Force meeting going on, so that's what has brought Joe into town. So it gives me great pleasure to introduce Joe Bonneau. So I've known Joe for several years. First met him because he took over my desk as a PhD student at the University of Cambridge. So right at the time that I graduated, Joe was a beginning student there, so we share a common advisor. Joe has done a lot of great work on very technical aspects of cryptography and cryptanalysis, beginning work he was doing at Stanford, and then he did his PhD in Cambridge, where he did a lot of other interesting work, getting into human factors, which is some of what I'll talk about today. After Cambridge, he worked at Google for a while, and was a postdoctoral fellow at the Center for Information Technology Policy at Princeton. And now he has a dual appointment as a technology fellow for the EFF and a postdoc in Dan Bonneau's group at Stanford. So sort of come back full circle to where he started. So very, very glad to have you here. And so Joe, the floor is yours.
Thanks. Yeah, I mean, I can add that people mistook me for Tyler for about a year after I went to Cambridge, because I think we were the only two Americans in the group, and people always told us that we looked so much alike they couldn't tell us apart. I don't know if you guys see that.
I don't really buy it, but I guess we don't look like British people. That's for sure.
Yeah. Anyway, yeah. So I'll be talking about some work that I did last year while I was at Princeton. So I put Princeton on here because this our main publication was at Usenix Security last summer with Princeton on it. But as Tyler said, I've moved on, so I'm now at Stanford and EFF. Right, so hopefully this will be a fun talk. The goal of this talk is getting people to memorize a really strong password using some tricks from the memory field. So the motivation, of course, at least one motivation that we see a lot of password leaks. So websites will lose a big database of hashed passwords. Attackers will then go and usually be able to break most of the passwords, try to use them at other sites. So this is bad. So like Tyler said, during my PhD work, I did a lot of research on how strong passwords actually are, what's the right way to model that, collecting data, try to put a really good number on how strong passwords that people choose actually are. It turns out that's actually a more complicated question than I think anybody appreciated before I started doing that work, but the short version of it goes like this. Basically, if you're trying to say how strong or weak a password is, you have to quantify how much work the attacker is willing to do, or are they only targeting the weakest passwords, or do they actually want to get everybody? So this axis here is basically what percentage of the population the attacker is aiming to break. So here, if the attacker only wants to break the absolute weakest passwords in the distribution, the amount of work they have to do, and this is kind of a log scale because it's measured in bits, is very, very low. So around the intercept here is around 6 bits, so 2 to the 6, right? That's about 1 in 64. So what that means is that the most common password in most distributions is chosen by about 1 in 64 people, or usually more than 1% of people. But the attacker has to do more and more work as they want it to compromise a greater fraction of people. So what's interesting about this graph is that if you just gave people randomly chosen passwords, that would be a flat horizontal line on this graph, because there's no weakest password in the distribution. Every password is equally strong. So you can ask yourself the question, if we got rid of human chosen passwords completely and just replace them with randomly chosen passwords, from what size space would we have to randomly choose those passwords for this to be an improvement? And it turns out, even if you went with 10-bit passwords, that would be better than the weakest passwords. So you would actually be improving security for some people, and you'd be degrading security for other people. But for more than half of people, if you just went with a 20-bit random password, which is really not very much, that's just 6 decimal digits, that would be better than over half of people's passwords. So my conclusion at the end of all this is that we could switch to random passwords and it would actually upgrade security for a lot of people, and the size of these wouldn't be that big. I mean, in particular, a 6-digit decimal number, that's smaller than a phone number, and people have memorized phone numbers for a long time. So for a couple of years, I was really thinking, why is it not possible to get people to memorize a small random password? It's been considered sort of something that people can't do, even though demonstrably people do memorize random numbers all the time that are actually bigger than what it looks like they can't memorize in the space of passwords. So one digression I'll throw in here, which is my service I'm trying to do clearing up, because I think people just sort of concede to the fact that passwords are going to leak and then you can do cracking. That really shouldn't be the case. So the reason we're in this mess to begin with, the way most websites or most systems store passwords is they just hash the password with a constant hash function. That means that if the database leaks, an attacker can try as many things as they want. So you could prevent this problem if you could move the password storage to some secure storage. So I'm indicating in green here. Green usually means secure. This is some magic storage. Maybe it's in an HSM, so hardware enforced security, so that these hashes can never leak. So that's one design that would actually fix the problem, but people say maybe that's impractical because you have to store your whole password database in an HSM now. People don't want to do that. There's actually a much simpler solution. You really only need to store one small cryptographic key in secure storage, and then you can have a secure password database that won't leak. So if you're ever designing a password storage system and you have the opportunity, the right way to do it is not to store the hash of the password, but to store the MAC of the password, the message authentication code, and keep the key in secure storage. So I've been telling companies to do that for years, and it's basically never done. But if this was done, this whole talk wouldn't really exist in the same way. Anyway, that's just for the main use case, though, of logging into a remote server. There's other things people use passwords for where you fundamentally can't have secure storage, in which case having a really strong password is worth it. And it's worth asking the user to memorize something strong. So if anybody uses PGP and you protect your private key using a passphrase, that's a good application where memorizing a strong password would really help, because the assumption is the attacker can get your private key file, and then they're going to be able to do as much work as they want. Also, if you use a password manager, often your entire encrypted database of passwords for every site, basically the same thing, password protected encryption. And also just kind of having any kind of single sign-on system or enterprise system where you have one account that unlocks everything else. It would be nice if we could just get people to memorize one really strong password and then protect against all kinds of guessing attacks. So the thinking is, whenever you're putting a lot of eggs in one basket, you want to really protect that basket. All right. So that's what motivated me to get into this. And now we're left with the question, what are the obstacles to getting people to memorize a really strong password? So this is kind of our joke slide about how brains don't work. They aren't like hard disks. You don't get to just write whatever you want into people's brains. And in particular, the way this model fails is the assumption that you can just write some random data into somebody's head as if it's a hard disk, and then at an arbitrary time into the future, you can ask them to remember it, and they'll do that successfully. So human brains specifically don't work this way. There's actually really good reasons from an evolutionary standpoint why your brain doesn't just memorize random things that it's told. But I guess before getting into that, I'll just say that this is sort of the level of thinking that the crypto community had put into it, basically just assuming that humans can't do this. So this is kind of a classic quote that's been repeated in a couple of security textbooks, actually. That basically just declares humans can't remember cryptographic keys, and they have all these other problems, so we should assume they can't do it. So this is kind of the folklore that we were trying to debunk a little bit with this research. So a better model for human memory, rather than a hard disk, I don't know if it's the best model, but we'll go with it. It's kind of like erosion, where eventually you can form a really deep, lasting imprint, but only by basically trying to write into memory many, many times. So at a high level, the way people remember anything is just that they've seen it so many times before. So if you really want somebody to remember something, you have to just keep telling it to them, and eventually it will stick. People have a lot of flaws, but almost all people, except for people with fairly serious neurological disorders, have memory that works this way. Eventually, if you've heard something enough times, you'll remember it. Even though I think my joke here is that my mom disputes this with a lot of points of manners, because she said, I told these to you every day for 18 years and you never learned them. But in general, most people can memorize most things if you tell them enough. So intuitively, that's like a fairly straightforward concept, but it's actually been studied very rigorously in the psych community. It was actually basically isolated as a principle a long time ago, so in the 19th century, by this guy Hermann Ebbinghaus, who did some of the first really formal research into how people memorize things, how you can get them to memorize them more effectively. If you've heard of this guy's name at all, it's because the learning curve was a term that he coined. Although what he actually coined, which I think is more insightful, is what he called the forgetting curve. And the principle is pretty cool. He measured basically, if you tell people some random information and then you ask later on whether they remember it, the chances that they remember it, so this is averaged over a lot of people, will decline slowly. So there'll be basically this curve as people forget the thing that they were told. The neat thing is that when they forget it and you tell them, then they remember it again, and the slope of this curve becomes much, much shallower. So basically, with every successive rehearsal of the information, the forgetting curve gets shallower, which means that you're remembering it for a much longer period of time. So this basic principle is called spaced repetition, which really is just a fancy way of saying that you have to be repetitively told something. To the extent that it's more complicated than that, it's that the rehearsals have to actually be spaced out. So you can't just tell somebody something 30 times in 1 minute and expect to get good results. You have to space those trials out. And there are some actually pretty deep reasons for that have to do with how neurons work. When you remember something, a connection between neurons actually strengthens a little bit. There's actually a chemical reaction that happens. And there's a period after that where it can't strengthen any further. It's actually called the refractory period, which was kind of the giggle moment usually in this talk. But I guess this is a very mature room of scholars. But essentially, you learn something, and for about 10 to 30 minutes after that, hearing it again is not going to significantly enhance the strength of the memory. So you want to not only see something multiple times, but it has to be spaced out so long that this period actually passes and you're able to form a stronger memory the next time. So if you don't believe me that all this stuff has been figured out by the psych community, the alternate way I like to explain it is that people who have really high stakes to memorize something have independently discovered all of the same science. So this is just one program called SuperMemo that's kind of legendary amongst med students, in particular for memorizing all of the parts of the body and all of the blood vessels and everything else that they have to memorize. And you can see that it goes back quite a way. It's gone through a lot of iterations down to you can get it on your phone now. And you can actually do it for a lot of information besides medical information. People use it for learning vocabulary or geography or anything else. But it's fairly simple. It has the information you need, and it just has basically timers of when the last time you rehearsed it was. And it comes up with the best schedule to give you more rehearsals, so it will sort of buzz you and say, you know, time to re-rehearse what the vena cava is, or whatever the information is. And it tries to space out the repetitions optimally so that you'll learn the fastest. So still very popular. Everybody attests that it's just amazing how well this works. So if you're ever taking, if you're studying for a final with some really repetitive information, you can try this out. But yeah, there was some famous book about being a med student, and it said the two biggest tricks of the trade are super memo and amphetamines. Okay, so now I'll tell you what we actually did. Our goal is to try and get people to memorize passwords with basically the same idea. And we wanted them to not even realize that this was going on. So fairly simple interface. We started with just normal username and password. We said users can pick whatever password they want, so we're just doing normal user-chosen passwords here. But then after they typed their password, we asked them to do a second step, which was to type 2 words that were shown on the screen. So in this case, we would just show the words first and nurse, and the user would have to type it, and then they would be logged in. And we had only 2 treatments, which is fairly low for usability paper, but the other formulation we tried was showing it as random letters. So instead of the 2 words, some people got 4 random letters. Now the next time they came in, they had to type the same 4 letters or the same 2 random words, whatever they got, but now the hint wouldn't be shown right away. So there would be a half-second delay before they saw what they were supposed to type. So after waiting half a second, they would see the hint again, and that delay got longer, so every time they came back, we added an extra half a second. But when they figured it out and they realized that they were being asked to type the same thing every time, they would just start typing it before the hint was shown. So then we could really easily tell when people had actually memorized this information. And when they'd memorized it, we just added more until we built up what we thought was a strong enough password. So I think this link may be dead now because we actually ran another experiment recently. But well, you can try it out. If not this, then there's going to be an updated version of this. And I love the fact that we got this URL. My colleague Stuart Schechter at Microsoft Research said, you know, he was able to register this, and I asked, does that mean nobody at Microsoft Research has ever run an experiment before? But that's what we got. Okay, so that was our design. Then we asked, how big of a code do we actually want? How, you know, we could get people to do this forever, but at what point is it kind of overkill? So this is fun security digression number 2. I claim that the best way to actually measure how expensive brute force or password cracking is now is to look at Bitcoin. It's basically a giant system where people are paid to do brute force work. So through some fairly simple calculations, you can look at over time how much money all of the Bitcoin miners collectively made and how much work they did. So this is a little out of date, but it actually has leveled off a lot as of the end of 2014. But basically you can say that the miners made a certain amount of money, they did a certain amount of work, and if you divide that through, we basically came up with 2 security levels. For about $1 million, you can do about 2 to the 70 work in a year, and for about $1 billion, you can do 2 to the 80. That's at the efficiency of the Bitcoin miners. We added in a little bit of security slack there because if you were one central operation with a really big budget, you could probably be more efficient than random people mining Bitcoin in their basement or their dorm room. But this is the basics of it as far as we know, unless somebody has a really dramatic advance in silicon that we don't know about. So how do we get from 2 to the 70 or 2 to the 80 to 2 to the 56, which is what we actually used? So you can stretch this by using a slow hash function. So if your hash function is really 2 to the 14 iterations of SHA-256 or whatever you're using. The attacker has to do that work, so you get to basically subtract that from the length of the secret that the user has to memorize.
So your analogy here is between doing a hash for Bitcoin and just trying a password? So this is for brute forcing a password?
Yeah.
Okay. So you're assuming that the computational cost of trying a password is the same?
Yeah, so...
Do you think that's pessimistic or optimistic?
Well, I mean, you can pick your hash to be whatever you want. If you just used SHA-256, which is what Bitcoin uses, then it would be exactly 1-to-1. But we're assuming that you can realistically, it's not that hard to do 2 to the 14 iterations even on a live login server. So then that basically means that the task you're asking the attacker to do is 2 to the 14 times harder, which is why you can scale the length of the secret down a little bit. So that's what's going on here. So anyway, just a fun exercise. Bitcoin basically provides a really nice spot market to figure out how expensive brute force is, which is nice because there's a lot of older papers which basically speculate and try to figure out how much chips would cost, but Bitcoin is basically just a market price for it. So that's how we got to 56 bits. Once we decided on the security level, there's a lot of different ways to represent that random information. Probably the most naive would be to just have it be literally 56 bits of ones and zeros. We didn't actually ask any users to do that. But the point is there's a bunch of ways to do this, from kind of most low level in bits down to just having letters, having lowercase and uppercase, actually having words. There's different sizes of word list. There's some more advanced projects going on right now to try and actually generate random text or even poems. We didn't test any of those in this experiment, but they're out there. We only picked 2. So like I said, we picked lowercase letters, in which case you need 12 lowercase letters to get to 56 bits, or words chosen from a very short word list. So this word list, everything was 3 to 5 letters. We made it ourselves. We basically just picked 3 to 5 letter words that weren't too vulgar because we were asking participants to memorize them. And we did have the nice property that none of these words are prefixes. They are actually all at least at a distance 3 away. So if a user has one typo when they're entering the word, you can actually fix it automatically with no security loss. Anyway, so that's probably too small a font to see in the back, but we have it all online, and it's actually, I will say, this is a little bit of an understudied research problem, exactly how you choose this list. So we had to make it up on the fly for this experiment. All right, so that was our system design. Of course, we wanted to test it, so like all usability researchers now, our first port of call was to just do an online test with Mechanical Turk. This is a little bit of an unusual test because we wanted people to interact with our system over time. So we had to pay them $19, which is astronomical for a Mechanical Turk experiment. Usually people get paid 5 or 10 cents. The reason, though, is that we asked them to log in repeatedly over a period of 15 days. And we initially asked them to do up to 90 sessions. We lowered it to 60. And they had to do them at least a half an hour apart because we wanted that spacing effect. So like I said, we didn't want people to know that this was actually about the password, so we had to come up with some reason why we were asking them to log in so much. The reason that we gave them a cover story that this was actually a psychology experiment and we were studying how attentive they were at different times. So every time they logged in, we asked them to fill out this short survey. How long had they been awake for? Had they had any caffeine or anything recently? And then we had them play an attention game that measured their reaction times. So all the participants thought that we were just psychology researchers, and it's fairly plausible. If you ever go on Mechanical Turk and sign up for experiments, most of what you get are psych experiments. By the way, if anybody's interested in doing research, you should definitely go through the exercise of signing up as an MTurk participant. It will give you a lot of insight into how to do these. So before I did this experiment, I set out to make $5 on Mechanical Turk as my goal, to feel like I'd really experienced what it's like to be a participant. And that was hard. It took me like almost 3 hours to make $5 of constantly working. But it was worth it because I learned a lot. I would encourage everybody else at some point if you get a chance to be an MTurk participant. Anyway, so that's what users were faced with. They thought it was a psych experiment, but there was this password stuff going on in the background. And we just gave them a very short pop-up that said, we've had some problems with stolen accounts. Since this is a very highly paid experiment, we're adding this extra security factor. And finally, when they had memorized the whole thing, we just said, congratulations, you can type this on your own now. You've memorized it. And like I said, they would get locked out so that they couldn't do all the experiments in quick succession. They had to actually have the spacing come into effect. So we went into this not having any idea if it was going to work at all, if people would get the system. So fortunately, most people got it. We had a small number of people who quit like immediately after just 1 or 2 trials, but basically people who survived 1 or 2 trials basically stayed to the end of the experiment. Even though they could quit at any time, and we actually paid them even if they quit. There's kind of a funny ethics thing where you want people to finish the experiment, so you sort of tell them they have to finish to get paid, even though you, for ethical reasons, have to actually pay them if they quit at any time. So that's a secret of the pros I learned, is that it's not ethical to not pay people if they leave, because they should feel like if they're at all threatened or concerned that they are free to go. But you sort of hide that fact so that they are motivated to actually finish and you get good results. Anyway, so most people finished. The people who dropped out, more people did drop out who were getting the random passwords than in the control. So we did introduce a slightly higher dropout rate. It wasn't statistically significant, but it was a little bit of a concern. But about 75% of people finished the whole thing. And of those, almost all of them actually were typing the whole password from memory by the end of it. So most of them got all of the words. Of the people who didn't get all of them, most of them actually never even got the second one. And when we drilled down and asked them what was going on, we were actually surprised to see that they were very open about it. They said, I figured out what was going on and I just didn't want to do it, so I committed to never typing the word from memory so that you wouldn't give me any more. Like another thing that will really surprise you about doing these kind of studies online is you think you're not paying the people very much and they have no incentive to write anything. But if you ask people questions, they'll write very long and actually kind of insightful things. And the level of grammar and spelling is, for the internet, like very, very high. So, I mean, you see some like LOL and all caps here, but people actually say pretty sane things and give you good feedback. So that was good to see. But basically, these people said, we figured out what the experiment was. We didn't want to do it. In the first draft of the paper, I called them the conscientious objectors. But that was kind of like struck down by the peer reviewers as being not friendly to the users. But I think that was actually the right term. I mean, basically, these people just refused to play ball. That actually can sort of be an issue on Mechanical Turk too, is that you have a highly studied population because people sign up for a lot of these. So sometimes they try to figure out what the catch is in your experiment. But fortunately, we actually monitored a bunch of the forums that they went on, and we could see where they were posting about our experiment. We didn't interact with it at all because that would introduce some ethics issues, but we did check and see that people mostly weren't ruining the experiment for other people. So most people did it not knowing what was going on. Actually, the main feedback that we got, since this was relatively high pay, was people saying, you should sign up for this. This is a once-in-a-lifetime deal. You shouldn't miss out on this experiment because it pays a lot. All right. So this is a graph of how long it took people to memorize. So remember, we had 3 chunks of that 56-bit secret. This is how long it took people to actually memorize it and start typing it from memory. So this is the first chunk, the second chunk, and the third chunk. This is the percentage of people that have memorized it, and this is time. And you can see it's pretty good. By really about 30 trials, almost all of the people who are memorizing words had the whole thing. And the dotted line is people who are in the letters treatment. So you can see that it took them a little bit longer to memorize it. It's like shifted to the right a tiny bit, but roughly the same. So that was pretty promising. People actually memorized this faster than we thought they would. Another concern we had was, would it take them longer to memorize the later chunks than the initial chunks? Would there be some effect where basically their memory was filling up and they were memorizing more slowly as we went along? So I can show you this same graph, but we'll shift these three so that it's, instead of the absolute login number, it's the number of logins since you were introduced to that chunk for the first time. So a little bit of a confusing setup. But that's what this graph is here. This is for each chunk independently, how many logins it took to memorize it. And the blue was the first chunk here, so the opposite of what we were worried about happened. People actually memorized the second and the third chunk more quickly than they memorized the first chunk. So that was good, but it was basically in line with our understanding of memory that actually the total size of your memory is really, really huge. The problem isn't, it's a little counterintuitive because you think your brain's not that big, but it's basically impossible to fill your brain up capacity-wise. So when I showed this to, I presented this research at Princeton to the psychology department in one of their seminars, and they said, oh yeah, of course, like that's not surprising at all. There's no reason to believe your brain would fill up. So the computer science audience is usually kind of surprised by this, but it turns out the experts totally knew this was coming.
Hey Joe, quick question about that.
Sure.
Did anybody report the use of some aiding mnemonics that would help in the second and third chunks? They would turn one of the random letter phrases into a passphrase or something.
A couple people said that they had like come up with a story around the words,
right.
But we didn't specifically ask that, so we only heard people who volunteered in the debrief. But yeah, that could be a reason why it was getting easier as it went along. Okay, so the real test though was that again, people didn't know this was a study. We were trying to get them to memorize it. So 3 days after the study was finished, we emailed them and asked them to come back for a follow-up. Most people did because we paid them more money to do it. And we asked them in the follow-up, and again, most people memorized the whole thing. But we asked in the follow-up for them to type the thing from memory, their random code. And we also asked people if they had written it down, and we said if you wrote it down, try to remember it. And this was really, the crux of the whole paper was, would this work? Would people memorize it after a layoff? And we got really good results there. So overall, just short of 90% of people memorized it, and the people who got the words, it was over 90%.
Is that statistically reliable, 93 versus 82?
No. Good question. So the question is the fact that more people recalled the code correctly who got words than got letters, is that actually statistically significant? It wasn't. So we hypothesized that the words would be easier to memorize, and we saw some weak evidence, but it wasn't significant. So we were so excited about that we asked people to come back about 3 weeks later and see if they could still remember the whole thing after not having interacted with it. And now the recall went down to about 60%. So we were actually a little bit disheartened by that because it seemed like they were forgetting it pretty quickly. But again, actually, talking this over with the site community, they said, oh, that's actually totally to be expected because they'd only trained for about 2 weeks, and then there was a 3-week layoff. They were actually kind of surprised that more people hadn't forgotten in that time. It's not exactly this way, but basically if you've been using some information for time X and then you don't use it at all for the same period of time X, your brain will start to forget it at that point. But I should say that this does raise kind of some questions about suitability for some applications where you might have a long period where you don't have to actually use the password. So it is important that if you're getting people to memorize a strong password, they have to use it fairly regularly or else they will forget it.
So this is a follow-up to my mnemonic question. This would be a sort of an additional experimental condition, but did the people who reported that they used mnemonic actually have a better retention over time?
It was too small. Yeah, so, yeah. They were all people who like did fine, but there wasn't enough people to say much. Right, so a couple other details here. We were kind of hoping that the people who forgot it would have mostly remembered it, and when we drilled down, we would see they just sort of missed a letter or misspelled something. Turns out that wasn't the case. If we look at like which errors people had that could be fixable by the system versus ones that weren't fixed, most of the people who forgot it actually really forgot it. Like they only got one component or they missed the whole thing. It was only a pretty small number of people. The main error that we could kind of fix without hurting security too much is we could try every permutation of whatever they typed in. And that was like around 10% of people. We could try to fix up one component if they got like one word wrong of the 6. And that was like another 30% of people or so. But at that point, you're really hurting security because the attacker is down to doing like more like a 40-bit brute force plus whatever. So to be honest, you probably wouldn't want to do this unless you made the overall secret longer. So this was a little disappointing to kind of conclude that people who forgot it actually really did forget in a way that you couldn't help them.
But going back to your very first slide where you were looking at the bits for people's cell phone passwords, if I remember right, the y-axis didn't even come close to 40 for a while.
Yeah, so 40 would still be an improvement, but I mean, you could probably also argue that if you're bothering people with this system, you want to actually get them to good security. So how much did this actually bother people? The median delay that we added per login attempt was around 7 seconds, so not too bad if you're logging into a website. And the total amount of training time, if we added up all the time that we wasted of people, not including doing the attention game and the survey and everything else, was actually less than 12 minutes. So yeah, basically, it's spread out over time, but the total amount of time that you need to train is really, really small. A lot of people, suspect that people would have just written the code down. We can only take participants' word for it. They were brutally honest about everything else, so we assume that they were honest about this. But the number who wrote it down was, something like 20%. But what was interesting is that the people who wrote the code down actually had worse recall, which makes sense because they weren't having to memorize to recall it from memory every time they actually logged in. But the important thing there is that it wasn't making our results look any better. So if we threw out all the people who had written the code down, our results on memorability would actually look even better. So one thing that was pretty interesting when we actually went to Usenix and presented this work, we were in the same session as a paper out of Carnegie Mellon that was sort of a similar experimental setup. They let people pick passwords. They tested a bunch of different policies. And the neat thing was that they had people register passwords, and they asked them a few days later to come back and type the password in again. And this was user-chosen passwords, so people could type whatever they wanted. And they actually had a lower recall rate than we had in our study. So randomly chosen passwords with the training period were actually more memorable than user-chosen passwords with no training period. And I think that really speaks to the take-home message of this whole talk is that it's not really the fact that user-chosen passwords have a lot of structure that makes them memorable. It's that people pick something that they've already memorized. If you actually really force people to pick a new password that they've never used for anything else and isn't tied to some other information that they already have in their brain, they aren't going to memorize that password any better than a machine-chosen password. And we went back and looked in the literature actually at a bunch of studies that had looked at random passwords, and it all tried to show that random passwords were less memorable than user-chosen passwords. And we basically found about 5 papers that had done some form of this experiment. And every one of them concluded that they couldn't actually show the effect that they were trying to show, that randomly chosen passwords were less memorable. They all basically said, well, we sort of saw a weak effect, but it wasn't statistically significant. But when you string all the papers together, the story becomes a little bit more clear that really the only thing that matters is training. I mean, letting users choose something definitely helps memorability a little bit, but not nearly so much as letting people train. Right, so those are some of those papers. So, I mean, I guess the conclusion going forward is that this happens a lot in computer security, that people take not a very friendly attitude toward people who have to actually use the system. So the first sentence of this quote is probably the most famous one, that humans are incapable of doing this. And the last sentence, that we should design around what humans can actually do, is kind of forgotten. But we would push more for the latter thing, because people can actually do some pretty neat things when you give them the right interface to make it easy. So like I said, that means having a training period. People can't memorize anything without training. So it sort of requires a rethink in how we do authentication in general, away from the model where people enroll once and then they're fully secure from then on. It's worth accepting kind of an intermediary period where people have enrolled but they haven't learned the full secret yet. So you have some weaker authentication mechanism like a human chosen password. Or you do something like make them log in with an SMS code every time, and then you switch to the higher security period. So there's a bunch of different ways to improve this, some of which are already underway, which has been exciting. I think 5 different research groups have talked to me now about follow-up work that they're doing on this. So probably the most exciting, that's been the most exciting part since this research has been published, seeing people say that they want to cite it. So some of the work that's being done trying to optimize this, so we explicitly didn't optimize at all. We didn't try to make it particularly clever or friendly. We kind of just picked the words very basically. So a couple different groups are looking at how can we pick the words so that they're easier to memorize, what's really the right balance between words and letters, how big the word list can be, how many training periods does it really take, at which point should you add more pieces to what you're asking users to memorize, so all of that kind of stuff. Trying to make this work on touchscreens. I mean, I actually think unlocking devices is one of the most important user authentication problems right now that we don't have a very good solution for. The system we presented here isn't immediately very good for touchscreens, because slowing somebody down by 7 seconds on the web it's not good, but it's maybe not like completely impossible. But if you add 7 seconds to every time someone takes out their phone and wants to read the latest email that they got, people will go crazy and they'll refuse to use the system. So there's a lot of work on trying to kind of scale this down in a way that it can take like less than a second to do the training, so that every time you pull your phone out, it's actually training you to memorize a stronger password. And there's also this idea of, instead of waiting until the user comes to log in to do the rehearsal, actually actively pinging the user and making them type their password in, not for any security reason. Well, not because you need the security right then, but to train them to memorize a better password. So there's actually been some work dating back to before our research on how you might think about doing that. And there's a lot of other memory effects. So basically, one way to think about this research at a high level is we took the simplest and most well-known memory trick, this spaced repetition, and applied it to passwords. There's a lot of other memory effects that are really well known, that have been established in dozens of psych papers, that aren't being used to help people memorize passwords at all. So just lots of I think really what will be cool and exciting follow-up studies, or maybe just different studies on using these kind of effects. So that's it. I am happy to take questions, because I think we have some time, and these are all people who helped us along the way with the research.
Questions?
Yeah.
So do you measure the entropy of all these joint passwords when you construct?
Sorry.
The entropy.
Joint password.
The joint password.
What do you mean the joint passwords?
When you extend with chunks, like you have two transitions, so you measure how much entropy increase is happening. And the reason for asking is I would think people can memorize passwords if the entropy is low.
If the entropy is lower?
Yeah.
Yeah, I mean, well, the entropy was 56 bits for these passwords because they were drawn from a uniform distribution. I'm not sure I understand what you're getting at.
Well, if you're using chunks like that,
Uh-huh.
it's not truly random, is it?
Yeah, I mean, the chunks were randomly chosen, so. Like, you mean in terms of like, because they're words and they're not just random letters? Yeah, so the words were chosen randomly from a dictionary, so there's 2 to the 56 possible sequences of 6 words, and we picked uniformly over that set. So there's no correlation between the chunks. They were completely random.
Right. If somebody says I can remember or memorize a chunk as a word, that means it's not truly random.
I'm struggling a little bit with your question. What's not truly random?
Tell me one word you use as a chunk, an example.
What's one of the words?
Yeah, one of the words you use.
Cool.
First. Yeah.
Yeah. So if I can memorize those as words like that first or two, to me it's not truly random. There is some kind of a pattern there, which helps me remember that, right?
Yeah, I mean, I guess we could get into a long discussion about what it means to be random. I would define it for these purposes as like there's a large space of possibilities, and we picked uniformly from all of those possibilities.
Yeah. So the basic question is this: what is the difference if I come up with a passphrase instead of choosing from your chunks? How will you say that that's worse than how I create the passphrase from you?
Like if the user just picks a passphrase, well, I mean, in that case, we don't have a good model of what the distribution is, right? We can't say that the probability of what the probability from the attacker's point of view is of any specific passphrase, whereas in this system, since they're randomly chosen, the attacker knows the probability of any specific sequence is exactly, 2 to the minus 56. Whereas for a passphrase, we don't know. I mean, I did a lot of work on modeling those distributions, but fundamentally, you just don't have a compact model of what the user-chosen distribution looks like.
We know from your first slide what that distribution is like.
Yeah.
And we know that.
Well, yeah, you really only know like the more common things in the distribution. Like the more rare things, there's not enough data, so you don't know what the whole distribution looks like.
So it's very fascinating research. I'm wondering is that human is sometimes irrational, right? So it's a matter of security and usability, and people we don't like to memorize or having high cognitive load, right? So, but in this paper they have extrinsic motivation because you pay them to do, and they force them to do. But in terms of implementing in a real application, they might feel like, oh, this is too much work. I don't want to use the system. If they willing to memorize those passwords, normal password, they would pick the good one in the first place, right? So what is your ideas to address those usability?
Right.
Your plan
That's the point is well taken. That this is really only something that you should use in high security applications where the user probably wants to do it. So, I mean, the interest that we've gotten so far has been from like a couple of messaging systems and people who make PGP clients for passphrase encryption, for password-based encryption, and maybe those are users who have like more motivation. I mean, I probably should have disclaimed much more strongly. This paper, we're not attempting to solve every problem with passwords. If every website on the internet that asked you to register a password tried to switch to this system, that would be that would be a disaster. I would really not want that to happen. It would be really painful if you had to do this, for all these different websites. It only makes sense for the most secure ones. But yeah, beyond that, I feel like users would probably be a little resistant, so it would help if there was some like a company forcing them to do it. But I also think, having done this myself a bunch of times now to memorize passwords, it's definitely like a little bit of a pain to get started, but it's pretty cool how quickly you memorize it. And we actually got a lot of feedback from users saying that they were kind of like impressed with how easily they remembered it after the repetition, and that they liked the system by the end of it. So I agree that we'd probably have a marketing problem, but I think people will be won over because it ends up not being too hard.
So I have a following questions too. Like we shoot words and letters, right? And you also have some kind of poem stuff. And a human tend to, remember like rhyme words and poems. So what is the reason that you don't choose the poems and use the words and letters instead?
Oh, why didn't we use the poem? That's a good question. The reason is that there's a couple of people who have projects on the internet that do the poem, but they're not particularly mature. So we decided from the standpoint of this research, we just wanted to do the simplest thing, so it was kind of inarguable. And we were actually also trying to make the point, like the fact that the letters didn't do very much worse than the words was actually, I don't see it as a failure. I think it actually drives home the point that people can memorize the information in almost any format given the training. So we felt like if we went with the poem, people would think the effect was specific to poems. And our point was like, basically, if we tried to get people to memorize the 56 bits as ones and zeros, that probably would have failed. But almost any of the other formulations, I think, would be successful. So that's why we didn't want to use the fancy one.
All right, thank you.
Yeah.
Just a follow-up question about that. So I didn't look at your experimental design, and I don't know what your sample size was, but there was certainly an indication that word performance was better than letter performance. If you doubled the sample size, don't you think it'd be statistically reliable?
Yes, at the sample size we had, which was about 500 people total.
Oh.
That's
a big number.
Yeah, it was a large sample size. If we
there was certainly a suggestion that the results may be
I think at the same rate, if we kept the rate constant and doubled everything, then it would have passed all the statistical tests. But that's actually easier said than done here, because we did spend a research budget of like a few $1,000s on paying participants, because it's $20 a person. So I guess, would it be worth it to do a follow-up with twice the sample size to try to establish that point? Maybe. It's not a really controversial point, and like I was saying, it's actually almost a more important point that it doesn't matter too much between the two. So.
Quick follow-up though. This is the question asking portion. So, did you happen to ask any of the surveys or the exit interviews that whether or not they had expressed preference? How much they liked doing with words versus doing with letters? I know that they didn't have the choice, but if you asked them the same question about their enjoyment levels, did you see any difference there, or did you even ask the question?
We didn't ask the question, which I thought was a little bizarre. But the reason we didn't ask it is, I guess this is mostly my co-author had this opinion pretty strongly that it's not valid to ask participants directly if they like your system, because they basically, there's like a really well-known bias towards people saying that they like whatever system they're doing, because the participants want to please the experimenters. So it's considered unreliable, which is why we didn't ask it. But we tried to tease it out through other things, like the fact that the words had like a lower dropout rate and stuff like that.
Anybody else got a question?
Yeah, sure.
Could I ask, was there a reason you picked letters over hex? Just in my mind, I feel like hex maps easier, so I was curious if there was a reason you chose letters.
We are a computer science seminar. I was going to explain that.
I don't know if it's a bad question.
So I mean, the set of letters is larger than hex, and the concern was that hex introduces possibilities of people getting confused visually between some of the numbers and if they're letters, because I think normal users don't know that the space of allowable letters in hex is only A through F, so they might think that the 1 is really an L. So that's the reason we avoided it.
Brett?
Has anybody ever told you like Tyler Moore? No. No, my real question is, you've offered up a lot of sort of pros of this approach, and it's fascinating. Would you say one of the cons would be with the memory people tell you is retroactive or proactive interference? So presumably you want more than one random password.
Yeah.
And if I'm learning a random one, and I'm going to have a harder time learning the next one, a month from now or something, they start interfering with each other. Is that a con?
Yeah, it's definitely a con. There's a limit there. Although so Jeremiah Blocky at CMU he actually just finished an experiment, which is in his PhD thesis, where they did this with interference. And they actually found that there was no decrease in performance with people who were doing it 3 times simultaneously.
Oh.
So my feeling is that people could do it a handful of times without strong interference effects coming into play.
But if it got more than that?
Yeah, I mean, I've definitely done it to memorize passwords for different systems and been fine. I mean, I wouldn't want to extrapolate too much from that, but my feeling is even if you just think back to how many telephone numbers did the average person in 1990 know off the top of their head, which are a little bit smaller than this, but not that much smaller. I think you could get to a dozen before you were really in trouble from interference. Hopefully enough. I mean, if we're asking people to memorize more than a dozen passwords, that seems like too many. Yeah.
So if you were to use this, you're saying the application would be for the really important security websites. But if they're teaching them how to memorize it, where do you store it? In that case, where would you store these values?
Right.
It would be secure.
So that's a good question. So during the training phase where you have to be able to give people hints, yeah, you have to store it. If you're doing it on your phone would have to store it next to the password. And then the idea is that once the user has actually finished SMU, once the user has actually finished memorizing it, then you would destroy it. But that's definitely a vulnerability that you could lose it at that point. But I mean, in the traditional system, you could lose the password hash alongside it, which you would delete once you switch to the random password.
I'm just wondering, what is the range of this research? Only US-based or worldwide?
Good question. The participants were all US-based, which is actually, it's not, I mean, people could try to lie about it, but to sign up as a worker, you have to enter a social security number for tax reasons. So they've done some meta studies on Mechanical Turk. The feeling is that if you limit to US, you actually really are getting US-based people.
Yeah, because I'm just wondering, English has only 26 letters, but maybe Chinese has 5,000, Japanese has more than 5,000.
Yeah.
Hebrew has 40, 41, Arabic has 40 letters. Russian has 36,
right,
and other language has a lot of letters, so maybe...
Yeah, so it would be interesting to do it with an Arabic population or a Russian-speaking population. I mean, the difference between 26 and 30 or 40 in log space is not very big, so it wouldn't dramatically change things. Chinese is also pretty interesting because then it actually really is a lot bigger. There's actually been a couple papers last few years about Chinese passwords, which are interesting. Most Chinese speakers don't actually use Chinese characters in their password. Yeah, no, there's pretty good evidence that Chinese speakers and Japanese speakers and other East Asian languages don't actually use those characters in their passwords. So I'm not sure it would immediately work here.
Can I ask one final question?
Yeah, I'll have one too.
Sorry.
I could say, I mean, we would have to come up with a different word list, which is why I think research on word lists is probably a good topic because right now they're mostly kind of handcrafted, and coming up with like a good algorithm where you can just automatically generate a word list in Indonesian and then one that works in Mandinka in every language without like human effort every time would be pretty cool, I think. Because that's the bigger internationalization problem right now, is asking people to memorize the English words.
I'll just ask you kind of a related question, related to your research, but not directly. So a lot of the popular articles basically claim that passphrases are like random. Is there some good evidence about maybe a collection of 100,000 passphrases that you talked about and then measured them?
No, there really isn't, which would be, I mean, I collected a lot of data sets of different things during my PhD. We got one kind of smallish data set that was sort of like passphrases, but they only had a minimum of like 2 words. So we don't have a really good data set on how people pick passphrases. So it's basically an unknown. My suspicion is that the min entropy is probably still much lower than people think it is.
So what needs to happen then is people need to adopt your system and then get their database hacked and the passphrases leaked.
Well, but
then it'd be all random.
It'd be boring here.
Yeah.
What we need is like someone to somehow collect passphrases used for PGP. The problem is that they're all like distributed, so you never get a big data set, and passphrases are usually not really used in like a centralized system. Yeah, it's a big blind spot.
How do you think the tech-savvy nature of people that are naturally on Amazon Earth has influenced your study?
Yeah, that's something that you have to sort of write off in the limitations section and say, hopefully not too much. Yeah, that's like one of the noted biases in the MTurk population, is that the people are more tech-savvy than average. I guess I'd like to say there's nothing really specifically tech that would help them here. But yeah, we basically don't know.
Also age, what is the age, how does the MTurk population skew towards age?
So it's actually not, in other countries, like apparently in India there's an MTurk population that tends to be much younger. The US population is much closer to the median age for the US. So it's, I think, slightly younger, but by a very small amount.
Any other questions? Good. Thank you very much.